G'day everyone, my name's Matt and welcome back to a series of videos talking all about fire and fire behaviour. In today's episode we're going to be talking about convection, conduction and radiation, which are our three main types of heat transfer. Now when we're having a look at convection, conduction and radiation, we're going to talk about them individually, so we're going to have a look at how each of them work, but we're going to also look at how they affect each other, because they don't operate as a single entity when we're talking about a structure fire or even a bushfire or those sorts of things. They actually work together to actually spread heat through a structure or through any other sort of fire. So we're going to have a look at how they actually operate not only alone by themselves, but we're going to have a look at how they operate together as well. So we're going to go ahead and start with our first one. We're going to start with conduction. Now the definition of conduction is the mode of heat transfer associated with solids. So to demonstrate this, what I'm going to do is apply a blowtorch to this small steel box. And what we're going to see is as the heat starts to build, we'll actually see the heat move from the point of origin, from where the flame is actually touching from our blowtorch, and you'll see it spread out away from that point of origin throughout the steel box. And this is via the process of conduction. It's actually the molecules are physically touching each other, and therefore they're able to pass the heat on from one molecule to the next, and therefore the heat will spread throughout the steel box. Now this is particularly important for any sort of structure which involves a lot of steel. Now in our homes, it's not generally a really big way that heat will actually move around, because we actually don't use a lot of steel for our walls and these kinds of things. We may do it in steel sheds, but for generally in our homes, we don't use steel as a major building material. However, in ships and large boats and these kinds of things, it is a really common way that we actually do build these structures, which means that the conduction in the steel can actually be a really important part to how a ship will actually stand up to a fire inside it. And that's when we start to talk about things like boundary cooling and these sorts of things, because what we need to do is make sure those walls stay cool enough that they don't actually ignite things on the outside or in the next compartment. And to demonstrate that, what I'm going to do is just apply a piece of plywood just to the outside of this box, and this sort of just demonstrates what it would be like for something combustible on the outside of a room involved in fire. So you can see that quite easily it's bursting into flames, which just shows that it would be quite easy to spread that fire. Now to demonstrate that each different material has a different way that it actually spreads heat or different conductivity, I'm going to just apply the blowtorch to this piece of plywood, and I'm going to burn it for around about the same time, but you're going to get a very different result. Now straight away we start to see it charcoaling up, and some of these products are going to start pyrolyzing away and burning away, and eventually you'll start to see that we'll get a bit of crazing and that kind of thing in the area where I'm applying the blowtorch, and that's because all these materials are being oxidized away, and what we're being left with is just some of the more base minerals. But on the other side, on the right side of our picture, we're not seeing that same effect that we had with the steel. We're not seeing that discoloration, and this is because timber operates very differently than steel. Timber is actually very poor at conducting heat, and therefore it doesn't spread out nearly as much as it would with steel. And the effect of this is the timber actually keeps a lot of that heat centralized to itself, and therefore it breaks down and these sorts of things. So what we'd expect to see here is it will continue to break down until it finally burnt through. However, just to demonstrate that we're not getting anywhere near the type of conduction that we did with the steel, what I'm going to do is just run my hand up and down the timber, and you can see I'm not being affected in any way. It's still quite cold. So, alright, so we're moving on to radiation, where we see a different type of heat transfer. Now, thermal radiation involves the transfer of heat by electromagnetic waves confined to a relatively narrow window in the electromagnetic spectrum. Now, what does this actually mean? Well, when we think about electromagnetic radiation, a really good example is the sun. So you can see here that what I've got is a magnifying glass and a piece of plywood, and all I'm going to do is concentrate those waves into a single spot. And what you'll see relatively quickly is that these waves start to heat up that spot until it starts to pyrolysize and give off a small amount of smoke. And if I was able to actually create enough heat in that spot, I could certainly create a fire. Now, another couple of examples of this sort of heat is if we're standing around a campfire or something like that, or even sitting in front of a bar heater. The heat that we feel from these heat sources is actually radiation because it's travelling via electromagnetic waves. Another really important one for us is when we're inside a structure fire. As firefighters, we sit down and we get down below the smoke, but that smoke is really, really hot. And as it moves through the building, it also radiates energy back down on us. And this is a really key part of how fire and heat moves through a building. If we were to look at this picture here, what we're getting is our radiation from our fire itself, but we are also getting radiation back down from the neutral plane. So that's all radiating back down on us as it moves through the building. Now, this is really important because this leads right into our next type of heat, which is convection. Alright, so now we're moving on to convection. Now, convection is associated with the transfer of heat by the motion of a fluid. So, what is actually classed as a fluid? Well, when we're talking about fluids, we are talking about a substance that has no fixed shape and easily yields to the external pressure, so a gas or a liquid. So we can actually think about air and smoke and these sorts of things as a liquid. Now that actually helps because now what we can do is create an experiment to demonstrate how different gases or different liquids will actually behave when they're different temperatures. Now what I have here is a fish tank filled with water and a small container that I'm putting some food colouring into. And what I'm going to do to the food colouring is add some boiling water so that we have a temperature difference between the cold water that is actually in the fish tank and now the boiling water that's in our small container. And I'm going to add this small container into the fish tank and then release the boiling water. And what we should actually see is that the boiling water within the container should be more buoyant than the cold water around it, and therefore it should rise to the top. And this should actually really demonstrate what's going on inside a structure fire or any real fire when we're talking about our smoke. Because our smoke is much more buoyant, it's much hotter than the air around it, and therefore it rises up. And you can quite clearly see here that what's happened is our water has actually risen up and taken out the top layer of our fish tank. And this is exactly what we see inside our structure fires. We actually see the plume come up and then spread out, and that's what we're talking about with our neutral plane. And obviously as they start to mix, all of these gases, or in this case our water, they start to become the same temperature as the air around it, and then we lose our neutral plane. So it's a really good example of what's happening. Now a real world example is here, where we're inside a fire behaviour cell and we have our fire at the end. Our cold air is where our firefighters are sitting, and we can see the clear air going in. Now that's our air track being drawn to our fire. That's then becoming a part of the fire, so it's going through that chemical reaction, turning into smoke and other products of combustion, and they're being heated when they do. So when they're heated, they become much more buoyant, and therefore they rise up. And that's how we get this neutral plane that you're looking at, and the smoke is then, via the process of convection, travelling back through the structure. Another example where convection is really important is in the bushfire realm, where we can see that these convection currents can actually be so strong that they can start to influence the weather. And in some cases, they can actually start to create their own thunderstorms, which we call pyrocumulus nimbus clouds. I'll talk about them in another episode, but they can actually start to affect the weather around them and actually block the prevailing fire conditions. Now this can make it really difficult for firefighters and fire managers to actually predict what's going to happen, because the weather can be so extreme and so unpredictable under these conditions that modern firefighting techniques and modern firefighting prediction models simply can't keep up with what's happening. But that can be in another episode. Alright, so now we've seen that convection, conduction and radiation not only operate by themselves, but they also operate together to actually spread heat throughout a building or even in a bushfire setting. And that's especially the case when we're looking at the relationship between convection and radiation, where we've got that convection current where the air track comes in gets to our fire, the chemical reaction takes place, and all the superheated gases and smoke particles and all these kinds of things are released from our fire, and then they rise up and travel away from our fire in the form of our smoke above our neutral plane. And as that convection current moves away from our fire and spreading out through the building, the actual heat that is held within that convection current actually starts to radiate back down on everything in the room and in the adjacent rooms from the fire. And all these things start to then heat up. And as they heat up, as we know in previous episodes, they start to pyrolysize and break down. And they'll then start to emit more and more flammable gases. If there's enough heat there and the oxygen is present, then we have all the sides of our fire triangle, and we can then get our spontaneous combustion, which we also talked about in a previous episode. And if everything is actually heated around about the same level right throughout an entire room, we get that spontaneous combustion occurring throughout that entire room over a very short period. And that is what we've referred to as a flashover. I'm going to do an entire episode on flashover at a later date, but that's just a really good introduction to actually how a flashover really occurs. So that's it for this one. Just to look at the 3 types of heat transfer. Hope you enjoyed it. Thanks very much, and see you next time. Cheers.